that time of year again where sleigh bells are ringing, snow is glistening, and the lights have us brimming with joy, meaning that Christmas is almost here. Let us introduce you to Ted, who is CEO of Netflix, which is one of the key players in the streaming industry. He has approached you to seek advice from an expert in operational management. Indeed, when setting annual objectives based on rolling forecasts, he realized that the most important period in terms of profitability is Christmas. Thus, he wants to maximize revenue on his platform. However, some of his clients only want to see Christmas movies, while others prefer other genres. So how can we help Ted solve his problem? One way would be the usage of linear programming. However, what is it? Linear programming is a tool that one can utilize when making choices on resource allocation. It aids in management decisions on organizing resources effectively. By generally quantifying the amount of products one should aim to produce given resource constraints. Therefore, LP is nothing more than a maximum or minimum optimization problem. LP also has established assumptions and properties. In terms of assumptions, the following holds: linearity, divisibility, certainty, and non-negativity. A LP problem is therefore a deterministic model. Relating to the properties of LP, it consists of maximizing or minimizing some form of quantity. It contains constraints, provides management with alternative routes of production to best allocate limited resources, and is expressed in forms of linear equations or inequalities. Hence, how do we translate such inequalities into graphing a linear program? First, we must set up an objective function and its constraints. We have decision variables x1 and x2 with profits per unit of 70 and 60. To that, we create our objective function z given x1 and x2. There are two constraints projected as a linear inequality. One is inspection limited to 18 hours, and the other is the amount of storage limited to 42 cubic feet. We then must plot constraints on the graph, which requires simple maths. The feasible solution space where points fulfill the constraints can be found in the shaded region below the intersection between inspection and storage. Having identified this region, we then plot our objective function. By setting it equal to a number that can be divisible evenly by both coefficients, one can then apply the same method as in step 2. For maximization problems, one wants to find a line that is furthest from the origin and within feasible solution space to yield the greatest profit. In minimization problems, the feasible region is often unbounded. Thus, we draw a level cost line for minimum costs and identify the optimal corner point solution. The optimum solution would then be at the intersection of inspection and storage boundary. Feasible solution spaces often form a polygon with the intersections of constraints forming corner points. Coordinates of corner points can be computed to determine the objective functions at the points. One can then compare the different functions derived from the points to achieve the best one, meaning a maximum or minimum value for an optimal corner point. LP also has limitations and special features that include redundant constraints, infeasibility, alternate optimal solutions, and unbounded solutions. In real-world situations, LP is commonly applied to these 5 areas: food and agriculture, applications in engineering, transportation optimization, efficient manufacturing, and the energy industry. With the necessary theoretical knowledge on what LP is, we can now turn back to the problem facing Ted at Netflix.
Let's now have a closer look at how to solve Ted's problem in Excel. Here we want to know is how much of each movie type we should produce and release in order to maximize the overall December profit. However, we have some constraints that restrain us. These are resources constraints, such as how many people are available or how much time we have to produce a movie. We also have some special constraints fixed by the marketing team. For example, we cannot produce more fantasy movies than Christmas movies. I invite you to pause the video now and carefully read the exercise to have a better idea of the problem as well as the different variables and constraints aforementioned. Now we can start solving the exercise. To understand how this entire text can be translated into a simple Excel solution, we must first look at the decision variables, which are represented here by each possible movie type. We put in yellow the quantities of each movie type because we don't know them yet, but when we run the solver, they will appear here. Then, the objective function is what we try to maximize. Here, it's the profit. And its simple formula is to multiply the quantity of each movie type by its forecasted profit. We use the sum product function to make this formula simpler, so quantity sales times the price sales gives us the profit. Finally, we have the constraints. We listed all the constraints in a tab. In the middle, you have the quantity of resources needed for one movie type. For example, let's take the advertising cost. Each rom-com costs $3.2 million in advertising cost. All these given data are based on past performance and industry knowledge. Now, at the end of the tab, you have this part. The left-hand side is the aggregated sum of all the resources used. So if you take again the advertising cost and multiply the advertising cost of rom-com by the number of rom-coms we produce and do that for all movie types, then we have the total cost of advertising. Once again, we use the sum product function to make it simpler, but don't forget to freeze the quantity line, otherwise you will have an error in your calculation. To make it more understandable, we have a column with the sign of the constraints in the middle. On the right-hand side, you have the limit available resources, so it is basically the constraints you can find in the text up here. For example, we want to spend at least $21 million in advertising, we want to produce less than 2 rom-coms, and we want to produce less fantasy movies than we produce Christmas movies. Because we don't know the quantity of Christmas movies yet, we just plug the cell here and the quantity will appear once we run the solver. Speaking of which, I think we are ready to solve, so let's open the solver. So now when we open the solver, the first thing it asks us is the set objective. Here it is the profit maximization formula. Then we click on the maximization because that is what we want to do in this exercise. And then it asks us the changing variable cells. Here it is the optimal quantities of each movies that we want to produce to be able to maximize the profit. The next step is to set the constraints. Here we have already set up the constraints for you, but if you want to add a constraint, you just click on add, and then you put the left-hand side, you put the sign, and then the right-hand side, and you click on OK. Next step is to not forget to click on the box that says make unconstrained variables non-negative, because we cannot have negative variables, for example, because we can't produce negative movies. Then we cannot forget also to click on the simplex LP solving method, and then finally we can click on solve. So after waiting a couple of seconds, the solver tells us that they found a solution and that all the constraints and optimality conditions are satisfied. So here we just simply click on Keep Solver Solutions, and we can also click on the answer sensitivity and limits reports that we can add. But here, since we already have the sensitivity report for you, we will just click on the Keep Solver Solution. So now we can see that we get an optimal solution of 2 rom-coms, 1 animated movie, and 4 Christmas movies. Given those quantities, we also know the profit and the resources used. We can also see that the constraints that we have are satisfied. Now, the CEO of Netflix might be interested in having a look at the sensitivity analysis of this optimal solution. Indeed, the sensitivity analysis is a means of assessing the impact of potential changes of an LP model. Such changes may occur due to forces beyond a manager's control, or a manager may be contemplating making changes, say to increase profits or reduce costs. Therefore, it is a very interesting report to have a look at. First, let's see what would happen if we change the objective function coefficients. We can see here the quantity of movies produced, it's our final value, and the objective coefficient, which is basically our profit per movie. We can also see that we have 3 new columns. The reduced cost, which is by how much the profit is reduced if we produce 1 more unit of final value. So here, producing 1 more rom-com wouldn't lead to a decrease in profit, but producing 1 more action movie would, and that's why we don't produce any. We also have the allowed increase. It tells us by how much the profit can increase while the final value stays the same. And lastly, we have the allowed decrease, which tells us by how much the profit can decrease while keeping the same final value. This number here means 1 times 10 to the power of 30, so it represents infinity, and it means that even if the profit would increase to infinity, we would still produce only 2 rom-coms. In this case, it is because we have a constraint saying we need to produce at most 2 rom-coms. With this information, we can determine a range of values for which the optimal values of the decision variables will not change, called range of optimality. By subtracting the allowed decrease from the original value of the coefficient and adding the allowed increase to the original value of the coefficient, we obtain the range of optimality of each coefficient. So for example, for Christmas movies, as long as the profit per Christmas movie is between 55 and 64, the number of Christmas movies produced won't change. Finally, we can do a similar analysis with the right-hand side constraints. Here we have all our constraints, the final value of resources used with the optimal solution, and the right-hand side constraint details. Each constraint has a corresponding shadow price, which is a marginal value that indicates the amount by which the value of the objective function, so the profit, would change if there was a 1 unit change in the right-hand side value of this constraint. So here, if you increase the number of people by 1, the shadow price tells us by how much it would change the profit. In this example, it is 0, meaning that there won't be any impact on profit. We also have, once again, allowed increase and decrease, which tells us by how much the constraint of the right-hand side can change while the shadow price stays the same. Similarly, by subtracting the allowed decrease from the right-hand side and adding the allowed increase to the right-hand side, we obtain the range of feasibility of a constraint, meaning the range of values for the right-hand side of a constraint for which the shadow price remains the same. For example, if the number of filming days is between 4,212 and 4,515, the shadow price will remain the same. And with this, we conclude our exercise and our explanation on how LP can be solved on Excel.